Welcome to another summary video for Diploma Programme Physics. This time we are now talking about higher level topic 9, which is wave phenomena, and the first topic in that topic is 9.1 simple harmonic motion, which is a special type of oscillating motion which we talked about in topic 4. But what you have to know for the higher level content is that the so-called defining equation for simple harmonic motion is the acceleration is equal to the negative of the square of the angular frequency times by the displacement. So a is acceleration, x is displacement, and omega is angular frequency, which is the same as 2 pi times the frequency or 2 pi divided by the period. And it's measured in radians per second. So when you're working with simple harmonic motion and the angular frequency, always use the radian setting on your calculator. So therefore, if we had a plot of acceleration against displacement, which we saw before, we know from previously that it should be a straight line going through the origin with a negative gradient, but now we have to know that this gradient is equal to the square of the angular frequency. So now for the higher level simple harmonic motion, you have to be able to solve problems using the equations of motion, not only the graphs of motion. And there are two sets of equations which you have to know about. One is if the object starts to rest, i.e. from its maximum displacement at time 0, in which case the displacement x is x0, which is the initial displacement or amplitude, times the cosine of omega t. Omega is the angular frequency, time is the variable here. If we take the derivative of the displacement, we get the velocity, which becomes negative omega x0 sine omega t in this case, and acceleration is negative omega squared x0 cosine omega t. Notice that these two equations are the same apart from the omega squared. An alternate form for the velocity is negative omega times the square root of x0 squared times the displacement x squared. This you get out by doing some fancy trigonometric identity, which I'm not going to go through in this video because this is just a summary video. However, if the object starts from its maximum velocity, i.e. the displacement is 0 when time is 0, then there are another set of equations which you have to use. X becomes x0 sine omega t, v becomes omega x0 cosine omega t, and the acceleration becomes negative omega squared x0 sine omega t. Now during simple harmonic motion, we have exchanges of energy between potential and kinetic. But because of energy conservation, then at any point in the displacement, then the sum of the kinetic and potential energies should be equal. So if we were to plot displacement on the x against energy on the y, going between the maximum displacement and the maximum negative displacement, then the red curve here would be the graph of kinetic energy, and its expression is a half m omega squared brackets x0 squared minus x squared, and the blue curve is the graph of potential energy, which is a half m squared omega squared x squared. And at any point in time, these two will add up. This one plus this one will add up to give the total energy. So ET equals EP plus EK, so the total energy equals the potential energy plus the kinetic energy, and at any one time the potential plus the kinetic will equal the total energy, which is constant if we have no losses in the system, which is what we assume is the case during simple harmonic motion. Then we have two classic examples of systems which display simple harmonic motion. That's the mass on a spring system and the simple pendulum system, and the equations you're given in the formula booklet are for the period of both of these systems. basically you can calculate the period of a mass spring system by taking 2 pi times the square root of mass divided by the spring constant k. And in the simple pendulum, its period doesn't depend on mass, and the period is equal to 2 pi times the square root of length of the pendulum divided by the acceleration due to gravity.